the topological analysis of asymmetric tensor fields on surfaces. Go ahead.
Thank you, Gary, for the introduction. Also, I'd like to just have a comment about this work. Some of the ideas behind this research started about 10 years ago. So it's great that our team, after 10 years on and off, finally pulled this one off. And I'd like to acknowledge my teammates, Bob sitting here, and Harry Ye, a fluid dynamics researcher, and Zhang, my colleague at Oregon State, and also our students who actually really make this happen. So we have talked about tensor fields a lot, but usually when we talk about tensors, we meant asymmetric tensors, which is for a good reason, because you do have a lot of applications. You have medical imaging, you have solid mechanics, geometry processing, like meshing, people even found applications in robotics, as well as computer graphics. So with all these applications in symmetric tensor fields, it's no surprise that somehow asymmetric tensors have received less attention from the visualization community. On the other hand, we'd like to emphasize that asymmetric tensor fields are also important. So this is the work that we did a while back. That was the last time with Eugene sitting here and Bob and Harry as well, on visualizing asymmetric tensor fields for applications in earthquake engineering. So this is a visualized data for simulated earthquake in somewhere in California, Southern California. And the usual image that people see is the one on the upper right, which is the vector version that indicates the ground displacement. However, the seismologist was interested in finding out some of the other type of motions, like when the ground was moving, were there rotations, spinning, and expansion happening at the same time? And there was some hypothesis that certain motions should happen. Yet these hypotheses were very difficult to validate with the vector visualization. On the other hand, once you go to the tensor visualization, which is the spatial gradient of the vector, then a lot of these motions become more clear. Similarly, you could visualize other types of vector fields, like the flow data you see in the cooling jacket. One of the challenges with asymmetric tensors is that they're very different from symmetric tensors. For example, you could have complex valued eigenvalues, which make the visualization much more challenging. And also, even when you have real valued eigenvalues and eigenvectors, the eigenvectors no longer form an orthonormal basis, which means that you can't just do what we did before for symmetric tensors, where you just show one of the two eigenvectors. You have to show both, which make things much more complicated. So we actually have a line of research on asymmetric tensors. Starting in 2005, also at VIS, by Zhang and Pang, they started this the analysis by realizing that there are complex and real parts of the domain where the tensors behave differently. And they also introduced the notion of dual eigenvectors for the visualization of tensor fields inside this complex domain. Following that, we also did some work with Eugene and Bob along the way and Harry for a lot of the analysis. But most of this analysis was point-wise. Basically, we're just saying, okay, at each point in space, what happened? What kind of behavior could there be? And after that, the research has sort of focused on designing meaningful perceptual glyphs. For example, by Cross et al., Setzer and Kindelman and Gerritz et al. 2012, we had some preliminary research on asymmetric tensor topology. The idea is somehow, instead of doing this point-wise classification, we try to divide the domain into regions that have homogeneous behaviors. And each region is then treated as a node in some graph. And two regions that are neighbors to each other will be connected by an edge in the graph. And the hope is this graph will somehow give you a topological structure of your data. And there were two types of classifications. One of them is called eigenvector manifold, and the other called eigenvalue manifold. And this gave us two types of graphs, as shown here. Now, that approach is a nice start, was a nice start, except that its application is limited. For example, it's only applicable to planar data sets, but many of the simulation data are 3D and their boundaries are surfaces. And how to do this analysis on surfaces is a challenge. Also, if you look at the actual graph here, it's a challenge to see how many nodes, even to count how many nodes there are, and how many edges. And that makes this analysis much less useful, especially when you're trying to figure out what are the real features and what is noise. So this is sort of the main issues we're trying to address in this paper, which is to move the analysis to 3D, to surfaces, and also to allow people to see a simplified graph like this. And the idea here is to try to capture the major features. Now, briefly review why we care about asymmetric tensors. Actually, Tobias did had a very good job. Thank you for that. Sort of bring up why we care about the flows and the vorticities. And usually when you have a vector field visualization, what you have mostly is the path along which particles travel. But when particles travel on the path, they actually go through other fundamental motions, such as rotations, expansion, contraction, and also pure shear. And this information, this additional information is very difficult to see from the vector field plot we have on the left. On the other hand, you can see this more easily with tensors, because that's precisely the information contained by the tensor. And how do you get a tensor from a vector field? Here's the idea. The idea is to take the vector field and compute the spatial gradient of that vector field. Now you automatically get a tensor field that contains the information we're interested in. Unfortunately, or fortunately, this tensor is no longer symmetric, which is why we care about asymmetric tensors in the first place. Now, an asymmetric tensor can be decomposed into the sum of three different components. The first one is volumetric change. This indicates how the particle is expanding or contracting as it moves. The second part is related to the vorticity that Tobias was talking about, which talks about how the particle is spinning. So as somebody moves, for example, the figure skater could be moving while spinning around herself. Yeah. And the last piece is the pure shear. This is also called angular deformation, which means that the volume of the particle is not changing, yet the shape is changing. A circle is turning into an ellipse. And this is all important information. For example, the shearing is related to ocean oil spill and all that. So the behavior of the tensor field is mostly determined by the interaction of these three components. When we talk about eigenvector manifold, without getting into all the details of that, let me just say that you could classify all the 2x2 asymmetric tensors based into four clusters. Here we show the two you can sort of think of this as a latitude on the globe. So if you're in the red zone, you're in the north hemisphere. For example, Vancouver is in that zone. We're in that zone right now. And if you go further south to San Francisco, then you're in the pink region. You're sort of nearly more like the equator than the pole, but you're still in the northern south hemisphere. Now, the red region corresponds to the complex domain, which means that a particle is going through more rotation than shearing. And once you get into the shearing region, then it's the opposite, where it's doing more shearing than rotation. And again, Tobias mentioned that it's important to differentiate between a clockwise and a counterclockwise rotation, and that's the story behind the North Pole, the North Hemisphere and the Southern Hemisphere. In the Southern Hemisphere, the rotation direction is the opposite. Okay, now once you have this classification, you can start again by classifying all the points in the domain, which is this is a slice of the simulation data. You can classify all the points based on the four types, and then lump the regions and build a graph shown in the right. There's a different classification, and without getting into the details of that, let me just say that there are 5 types now, and somehow the graph looks different. There are 5 colors, and you can build a graph by build a graph with these 5 types of nodes. So this is all good, except let's recall that there's some fundamental issues. One, how do you go to surfaces? So let me just briefly point out the issue with the surface. So on the surface, everything seems fine, but it's not. For example, if you have this mesh, which is kind of like the surface of a pyramid, and the base is hollow, so there's nothing in the base. And you have a vector defined at the tip, which is pointing in the direction of OC. And there's the vector 0 everywhere else. Now, when you try to generate a continuous vector field everywhere in this surface, what you want is this. This is sort of the implication by having that tip vector going this way. This is sort of the trajectories you would expect. But things can go wrong. For example, usually what we do is just to compute a piecewise linear interpolation. And in this case, we put the 4 triangles down and did that. And we got 2 of them doing great. But now we need to make sure along the edges the vectors are the same. Okay, so it looks like there are some issues. Okay. Therefore, at the end of the day, we have to come up with a different one. And this scheme allows us to compute this graph on the surface. And I will move forward to the multi-scale. And usually for multi-scale representation, there are 2 questions. What are the editing operations? And what is the scale? So for the time being, I will just only talk about the editing operations. For the isometric graph, usually we have one region surrounding another, and we call this annexation. The outer region eats the middle region. The second operation is to have 2 regions connected inside an envelope. Third operation, starting for eigenvalue graph, this is when you have 3 types of regions, and what happens is we can eliminate one of them. The fourth one is to connect 2 regions of different types together, and the fifth one is the opposite, which is to split them. And the scale definition and also algorithm details will be in the paper, so I'll refer people to that. Applications. In this application, it's important to eliminate noise. This is engine simulation data, and people can see in the left there is much noise. And after our multi-scale analysis, the graph becomes simpler, and also the user you can see the noise difference. You can also identify spots where the engineers need to pay more attention. The next application is about river, and in this data, the idea is can you spot some sort of underwater features from the top, from the surface. You cannot really do that with a river map, but after doing the simplification, you can easily identify the seal underneath the water. So to summarize, we have built a multi-scale framework for this asymmetric tensor fields, and as future work, we like to remove some technical things, but eventually we would like to go to 3D. We wish to thank a lot of people, our team, and also some of the other people, our reviewers, and the funding agency. Thank you.
Thank you. There's only time for one quick question. Oh, wow, yeah, you asked for your own. Cool.
Thank you, Bob.
Bob Laramee from Swansea University. I could be wrong, but is there any chance of applying some of the tensor field VIS to time-dependent tensor fields? I don't remember seeing that yet, but maybe I overlooked something.
I think there's definitely potential. If I remember correctly, at least one time I had Hogan and I talked about something like this. It was like a few years back. I'm not sure if his group might have done something about this. I know you have been doing some of the 2D and 3D glyph design. Not sure if this has gone to the time-dependent flows. So that I have to check the homework, do the homework to check.
Okay, thank you, Eugene.
Thank you.
And